Today we are going to see the last part of Unit 5. It's a very easy, very sure. This is the marks. They are called as PLDs. PLDs means programmable logic devices. Programmable logic devices. That means you have an option to program. We are purchasing some multi-gate, R-gate, some devices we are purchasing. It will perform only that operation. But in this, when we buy a chip, there are certain options where you can change the operation or you can put the operation what you want. You can customize. So that is the advantage of this PLDs. So programmable logic devices. Earlier we learned about the different digital ICs. What all we learned about the adders, about multiplexers, counters, comparators, shift registers, and so many we have studied. And they are all fixed functions. If it acts as a counter, it will act as a counter rule. If it is designed for multiplexer, it will work as a multiplexer only. I cannot change, I cannot make a shift register to work as a comparator. I cannot make the adder to work like a comparator. I cannot change. It is fixed. Meaning that function is built in by the manufacturer. The manufacturer will put everything and give us, and it will do only that function. There are two ways to design digital circuits besides using fixed ICs. One is AC ICs, one is PLDs. So we have fixed ICs, but we can also change. So that is application specific integrated circuits, which is called as AC ICs. Another one is PLDs, programmable logic devices. So these are the chips that can be programmed by the user to perform different logic functions. Whatever logic functions you want to perform, you can perform using the programmable logic devices. So why use programmable logic devices? The convenience is we can program or reprogram. If you want, you can change the program. If you want, you can put the program whatever you want. In just a few seconds, you can change the program of the IC. They offer more flexibility than the fixed ICs or AC ICs. So PLDs give you more flexibility and they allow easy changes. You can easily change. And this makes PLDs a popular choice for testing, especially for R&D, research and development. You can use this number of times you can reprogram. Depending upon the way you can program, they are classified into these are the classifications. One is PROM, yesterday we saw PROM. One is PROM, programmable, read-only memory. How many times you can program that? How many times you can program that? PROM. How many times you can program PROM? How many times I told you? How many times we can program this PROM? Manufacturer, we are buying from manufacturer. It comes to your company. You can program one time. You can program once. I told you a number of times as well. And then programmable logic character. Then programmable array logic, PLA, PAL. Then complex programmable logic device. Then field programmable gate. These are all the different PLDs. Different PLDs. And in our syllabus, we are going to see these two programs. And to some extent, PLA, PAL, we are going to see. So each type will have its own structure and use, but all allow you to design your own digital logic circuits. So all these things you can program whatever you want. So how here you have to remember two things: programmable logic array, programmable array logic. There is only a change in these two letters. But in the problem, when they give the problem, you should know in which you have to program and in which you have to program or. Another one if you have 0. So all these things will have AND gates and OR gates. So you can program means you can change the connections. In some cases, certain connections will be fixed. You cannot change. In some cases, you can change both. In some cases, only AND can be programmed. In some cases, only OR can be programmed. In some cases, both AND and OR can be programmed. In these three, what you can do, how you can remember which one is fixed and which one is programmable. That is very, very important for problems. You should not confuse. I tell you some hints what I remember. You can have your own way of remembering things. Okay. When the problem comes, I will explain it. So here you have this comparison of these things. Development cost, fixed function. So what happens to the ASIC? I told two types of PLDs. One is ASIC approach, another one is PLD approach. So development cost will be low in PLDs. And space required is less in PLD. Power required is less in PLD. Reliability means what? Trusting that particular device, how it will work, how reliable it will be, high reliability. Circuit testing, easy. That is why we are choosing this PLD, programmable logic devices. And modification in design, the PLDs you can easily modify, whereas in ASIC you cannot modify. The design security is 5 years. Design time is also less in years. So we are going for. So this is another comparison between design approaches. Next, what is PROM? Programmable read-only memory. Programmable read-only memory. So it is a type of memory chip used to store the data permanently. Why? How many times you can store? You can program. How many times you can program PROM? Only once. That is, from manufacturer you are buying and you can program once. And once you program, it is permanent. Once programmed, the data in the PROM cannot be changed. Please remember all this. This is the easiest unit where you can score mark. Unless there is a reprogrammable variant, maybe some higher cost, if they give you a second chance to reprogram, you don't know whether it is available in the market or not. Otherwise, you bring it from the manufacturer only once you can program. So this is how it looks. You have n address lines. You have n address lines. So 2 power n. For n combination, you have 2 power n input, you have 2 power n output. You know that. If I have one input, I can have 1 or 0. If I have 2 inputs, 4 combinations, like the 3 inputs, 8 combinations, that is 2 power n. N inputs, 2 power n combinations will be there. So 2 power n addresses will be there. 2 power n addresses will be there. And this is m data line. That means how many outputs we are getting from it. What is the size of your word? So the size of PROM is written like this. If you have n inputs, then you will have 2 power n addresses. And if the word length is m, then the size of the PROM is ROM or PROM is 2 by n by m. That means what? How many addresses and what is the length of your word? Word can be 1 bit, 2 bit, 1 byte, 2 byte, depending upon the output function. So that we will see when I am doing the problem. So this is how the structure. So the basic structure of the PROM. PROM has, see in textbook they have given a big sentence. I'll write it as points easy for you to understand. I'll send you these things. When you're studying also, you can write as points. It's easy for you to remember. So PROM has input lines and output lines. Input lines and output lines. Okay? If the input lines receive binary address, that means whatever I give them 0, 0, 0, 1, 1, 1, this is address. The output lines produce a word. Whatever I am getting here is a word. Here it is a 4-bit word. Because 4 output lines are there. I will get like this, something like this. So the output is 0, 1, 0, 1. How many bits are there in this? How many bits are there? Why are you staring at that, man? Open your mouth and answer. How many bits are there in this? So it is a 4-bit word output. The output word length is 4 bits. You get 4 bits of the output. Set of binary values that corresponds to the input address. So in this address, that word is stored. Are you able to understand? In this address, that word is stored. So each input combination is called an address. Each input combination is called an address. Each output combination is called as word. Very, very, very important. Simple. If they ask you about PROM, write this and show this diagram. So when the manufacturer gives you the ROM, all the fuses will be connected. All the fuses will be connected. And if you don't want this connection, you blow the fuse. Blow the fuse, that means remove that fuse. That will be your design. Again, you cannot connect the fuse. Once you are programmed, it is programmed. Clear or not? Please respond. So this is PROM. For example of 64 by 4. Yeah, this is just 64 by 4 PROM. 64 address lines. And 4 is the size of your output word. So whatever I explained, that is what is shown there. So PROM implementation, as I told you in this PLDs, you will have and R. These are the 2 components which will be there in the design. And OR logic. The input goes to the AND gates and then OR gates will produce the output. This is nothing but your combinational logic circuit. Sum of products. Sum of products. If you have f of a comma b is equal to sigma 0 comma 1. This is similar to that. So what we mean is a bar b bar plus a bar e. Isn't it? This is a AND gate. This is one AND gate. This is your OR. This is how this is done. So what you need to find is this one. The problem how they will give you. They will give this. Based on that you should find which are all the unternals and how many are required for each function. You have to give the condition. That's all. More than this, you will not get an easy problem in DSD. In digital system design, unit 5 is the easiest to score also. So here you have AND combination, you have OR combination, you have 8 fuses here. Already the manufacturer will put the fuse and send you. Whichever, depending upon your design, you have to remove the fuses. So this is how it works. So all those things, whatever we discussed, is there. This is one example of 4 by 2 PROM. 4 by 2 PROM. What is 4? We have 2 inputs. So n is 2. So if you have n inputs, how many address lines you have? 2 power. If you have n inputs, you have 2 power n address lines. So here you have 2 inputs. How many address lines I have? 2 power 2 is equal to 4. So 4 address lines. 4 address lines will be there. And here you have two function. So what is the word length? How many bits of output word is there? 2. That is by 4 by 2. Size how many right? Address lines by the number of bits in the code. So if I have 3 inputs and 3 outputs, what is the size? 2 power 3 by 3. That is 8 by 3 is the size of your DRAM. Any doubt? So AND matrix and OR matrix. This is what we are going to see here. This is how it will look. Internally, the matrix will look like this, and the matrix will look like this. So we are going to keep them fixed, whichever is required, whichever is not required, we will do this. This is double loop. So in our program, in our problem, how we will represent this from 1 up to 8, we will draw one line. We will draw one line and then give corrections to whichever you want by putting an into mark. This is relevant to keeping the fuse. If you don't put an into mark, that means you are blowing the fuse. Okay? The problem we will do it. This is OR matrix will look like this. So now we will come to the problem. This is how the example they will ask you. This is the problem. What is given here? DRAM. As I told you, how to remember what is to be programmed and what is to be kept as fixed. 3 problems you get. DRAM. How I will remember is DRAM you have in the word itself. I will take this. This is nothing but in reverse it is R. Okay, so R should be programmed. I will remember it, maybe meaningless. But I have to remember somehow, right? Then P, A, L. So the middle one. A should be programmed and B should be programmed. P, L, A. P, L, A is, I take this as all should be programmed. But it's not as well as I remember like all these two can be taken as all. I take it in the reverse form and then I remember like that. You decide how to remember, but you have to remember this. Otherwise, in the problem you don't know which one to program. In PRAM, R should be programmed. In PAL, center A should be programmed. This is something related to program and lock R. Something like that you have to remember. Here, program all. Here, program R. Okay? That you remember. In PRAM, what we should program? R should be programmed. So here, let us say this program. F1, F2. 2 outputs are given. What is the size of your word? 2 bits. Okay? What is the number of address lines? 3 inputs are given. 2 power 3. 8 by 2 DRAM. So this is the program. This is what is the answer for this. So let us see this. F of ABC is equal to 0, 1, 3, 5, 7. Okay? 0, 0, 1. So here we have to connect this F0, F1, F2, F3, F4. These are all vectors. You know that A, B, C. So 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 1. So this is your M naught. So here 0, 1, 3, 5, 7. Sum of 0, 1, 3, 5, 7 according to the month. So here how they are already fixed, and is fixed, how we have connected 0, 0, 0. A bar, B bar, C bar. What you have to show in the diagram in the example. This should be dot, this should be into mark. That means into mark is showing that you can program. Dot shows that it is already programmed. Remember, very important diagram. Today's exam, whatever I am teaching you will fetch you 16 or 20 marks. And then everything 0, 0, 1, 0, 1, 0, whatever I have written, accordingly the corrections are to be given. Output is very simple. Whatever is there, we are going to connect that line and show us an input. Second one is what? 1, 2, 5, 6. M1, 1, 2, 5, 6. That's all. More than this, you will not get a simple question. Are you able to understand? So, A, B, C, D, you are taking normal as well as inversion. In practice, you have to practice, then you will understand. Then you have to draw the lines. And for every product term here, you have to 0, 0, 0. That means what? A bar, B bar, C bar. So those connections you have to put that dot. Finish this one. Come to the R. In R, you see the given problem. Whichever main terms they are put an into mark for that and bring that output F1, F2. That's all. So this is one. Take 3 round table you have to draw. 3 round table is same as how we write the combination logic circuit. F1, F2. 0, wherever they are given, there you have to put 1 and remaining should be kept 0. And then this is the ROM symbol. 3 into 2 output. The size is 8 by 2. Size is very important. Size is calculated how? If n input is there, 2 power n is the address lines and number of output bits you have to see. So address by output lines will give you the size of the ROM. This is another problem. What is the problem? Circuit accepts 3-bit binary number and generates equivalent XS3 code. So you have to write the inputs and XS3 code. 0, 0, 0. XS3 means what? 0, 0, 0 if you have, the XS3 equivalent is what? Add 3. No, only 0, 0, 0, XS3 is what is 0, 0, 1? Add 3. So with that you make this table. These are all your outputs. What is the size of this ROM? Input is 3. What is the number of address lines? 2 power 3, 8. How many outputs are there? 1, 2, 3, 4. So output line is 4. So 8 by 4 ROM. Okay, 8 by 4 ROM. So with this, you are connecting this 4 output lines. And whatever midterms are shown, you have to mark there. Okay? Then you have to write the DROM table as well as the sizes. Another problem. Combination logic circuit is ROM. They may ask ROM or DROM. Question. Then the circuit accepts 3 bits number and generates an output of binary number, square of the input number. Square of the input number. So 3-bit binary means 3-bit binary means what is the highest number you get? 0, 0, 0 to 1, 1, 1. What is 0 to 7? That means 7 square is what? 49. So you have to check how many bits you require to represent that 49. And then you have to set your output. You have to understand. Then remaining also. Like this, any question will come. Sometimes directly the function will be given, sometimes they ask you questions like that. So here also you have given the function is given. So binary to XS3. So all these three I have already studied. What do you mean? Here you are putting it in a wrong form. So you have some examples. Next is PLA. Programmable logic array. That means all can be programmed. All can be programmed and also can be programmed. This is the problem. F of 357, F2, 457. Implement using PLDs. This question you have to check what they are asking you to implement. Question will be same for all the three PLA, PA, wrong functions only. But using what we have to implement. If it is wrong, then all should be programmed. If it is PLA, all can be programmed. And can be programmed, all can be programmed. If it is PAL, only and can be programmed. Like that, we should be very, very sure about what is to be done. So here the function is given. You have to find here. You have to find the product terms. So first, after the function is given, because you have to program both and region, right? So we have to find the unters. So we have to reduce the function. So function 1, we have this mapping. You have one function. You have another function. Now sometimes what will happen? You will have common unters also for both the functions. So that is all we have to check. So this is F1, F2. Any doubt till here? Once the function is given, you can draw the K-map and write this. Next, this is what is called as PLA program table. PLA program table. So we have to program both and or. So I am going to put how many product terms are there and what about the or terms. So what about the product terms? I have AC. I have written AC. AC means A is in a normal form, C is in the normal form, and I don't have B here. So A normal form I put as 1. There is no B term, so I am putting a dash, and there is a C term. Okay? So in AC I have A, there is no B term, and C is there. Next BC. So there is no A here, so dash. B is in the normal form, C is in the normal form. Then A, B dash. Here C is not there. So C is dash. A is in the normal form, but B is in the complement form. So I have to put 0 there. Okay? Now and term is over. Now I am coming to the function, that is the output is what? OR. So in F1 what all I should OR? AC and BC. AC and BC. So 1, 1. I don't have this term A, B bar here. So I have to put dash. Next coming to F2. A, B dash. A, B dash is there. AC is there. So I have to put that table first. After putting the table, I have to make the connections. And is also into, R is also into, because in PLA, all can be programmed. All can be programmed. So, and also can be programmed, all also. This is the diagram. Any doubt? If you practice, you will understand. Very, very easy. Like this, any problem. Sometimes they give you the product terms. That time you don't have to do the table. Directly you can. So here they are given the problem. Then you have to find the answers and then know this problem. We see into XS3. So again you have to draw the came back. BCD to XS3. BCD means 0 to 9. So 0 to 9, XS3, you have to write the corresponding XS3. So you will have 4 outputs. 4 outputs. So remaining after 9 is don't guess. 4 improvements, 2 power 4 combinations. 16 combinations only you can use 0 to 9. Remaining on, don't guess, map it, get the equation product terms, write the PLD table, PLA table, and then draw this line. If you do, you will understand. But I want to teach you first and then you can practice. So 3-bit binary to break. These all will come from first unit, second unit. All those whatever we have studied, we have to bring this up. So I'll draw the game map, get the terms, then program it. All are same only, using PLD. Take game map, get the terms, and draw the table, and then draw the diagram. Any doubt? Now coming to PLD. Okay, till now PLD we have seen. So now coming to programmable array. So here and the known generator program and the known generator program. So this is how you have to draw it. That means R is already fixed. R is already fixed. We have to decide how many outputs we have. Suppose in the first output you have only 2 terms. If you select a 3, everything will be 3 only. But every output may not require all the terms. So if it is not required, you have to put a cross mark in the untouched. Means I don't want the untouched. So this will be a bigger problem actually. So this is the problem. So first step is what? Tailor. Get the errors. And here this is a table where only and is programmable. So we have to write what is programmable and then write the other. Then what happens? This is your table. In each you have to check how many unterms you have. 1, 2, 1, 2, 1, 2, 3, 4, 1, 2, 3, 4. So here we need 4 product terms slicing. First, here you have 4 product terms. Here you have 4 product terms. So what they are doing is they are taking W, A dash, B dash, C, B dash, A, B, C dash. That term is already available in your output as. So here they are drawing one more line W, W, that is they are bringing W instead of having more number of terms. They are utilizing whatever is already available. So that is also brought here wherever whichever connections, whichever outcome requires that there is. And only on this programmable, so for and you are drawing a line and connecting the dots. This is DCD to XSD. So DCD to XSD, we have to draw a K manner and then write the inputs and outputs, and then you will be connecting. So here is the difference between, this is also an important question. Comparing PROM, PLA and PLA. So AND array is fixed and OR is programmable. Here both AND and OR are programmable. Here only AND is programmable. Cheaper and simple to use, costly and complex than linear like PROMs, cheaper and simple. Then all midterms are decoded, AND array can be programmed and get desired midterms, AND array can be programmed and get desired midterms. Only Boolean functions in standard SOP form can be given. Boolean functions in sum of product form can be given. Any Boolean function in SOP form can be implemented using PLA. Any Boolean function in SOP form can be implemented using. So that's all, we have completed the syllabus. Only thing is we have done this once a time. It's going to be. So that's it. We have done with the syllabus, but we will be practicing.